So we begin by describing a fixed effects regression model. So to understand the fixed effects regression model, assume that we have 4 districts, say A, B, C, and D. And we collect the economic activity levels in these 4 districts that are XA, XB, XC, and XD. And we collect the pollution levels in the 4 districts. Now, over a period of 2000 to 2020 annual data. So that means each of these observations comes down to 20 years of data. So our panel data will be of the form XY, where we will have XA 2000, then XA 2001, all the way XA 2020. Then we will have XB 2000, all the way to XB 2020, XC 2000, all the way, and we have XD 2020. Now, similarly, Y variable will also be like that. Y A 2000. What is the value of pollution at that particular year for that particular district? So this is our panel data. So when we want to formulate a regression equation, we would simply write it as Y IT equal to beta naught plus beta 1 x IT plus epsilon IT. Now, what happens is that we are only considering the effect of X on Y, but there could be some other factors of X that can actually affect Y. And this is because we assume that there is a correlation existing between the error term and the X term. And this is because of the omitted variable. So what are we actually omitting? So we assume that each of these districts A, B, C, and D have their individual specific factors or characteristics. So A has its own specific characteristics, B has its own specific characteristics. Let's say that we call this as gamma A, gamma B, gamma C, and gamma D. So these specific characteristics are unique for each of these districts. And assume that these individual characteristics are time invariant. That means they do not change with time. Then our equation. Okay, so what happens? Okay, there are time invariant and then there is time variant that change with time but remain. There are some factors that actually change with time but are constant for all these entire districts. It's constant for the entire districts but change with time. Say a government policy that is a national policy, a national level policy. But at the same time, the time invariant could be the population of a particular district that is unique for that particular district. So these characteristics can actually impact Y, but and they can actually correlate or lead to a correlation with X. So the error term and X are correlated. So in order to solve this and to extract the effect of the variable X on Y, just to extract the independent effect of X on Y, we change the model to YIT equal to beta naught plus gamma I plus say lambda T plus beta 1 XIT plus. What happens in this model is that we have controlled for, this becomes the initial coefficient. And this we have actually controlled for these individual specific time invariant effects for each of these districts, and also those factors that are the same for the entire district selected, but they vary with time, like a national policy. So when we control for all these factors and then run a fixed effects model, we control for these factors by running a fixed effects model, then you're able to derive the impact of X on Y. And it cancels out, there's no more correlation between X and the error term. So assume that after running the fixed effects model, we get a beta 1 value of 0.4. So this implies that a 1 unit increase in Y leads to we would say that 1 unit increase in X would lead to a 0.4 unit increase in Y. So that means that for each of these districts, A, B, C, and D, within these districts, what is happening to the relationship, or what is happening to the relationship between X and Y, X and Y, X and Y, X and Y, is actually represented by this beta 1 equal to 0.4. What is happening within? Now, what is happening between? Say that you want to compare a particular district to the other one. Then we use a fixed effect regression model, and beta 1, 0.4, the coefficient, is valid for this too. Now, for a fixed effects regression model, we are actually controlling for the individual specific effects, and these specific effects can be time invariant and they can be time variant too. Then we also represent the within entity changes over time. What is happening within an entity and between, if you want to compare two districts. Another assumption of a fixed effects model is that there is a correlation between these individual effects that are actually existing in the error term and X. So now we need to control for that, and that is what we have exactly done here. So this is all about a fixed effects regression model. Now, a random effects regression model. Random effects. So when do we run a random effects regression model? So there, in the same example, we have 4 districts. And these 4 districts, we measure the economic activity, that is X, and pollution levels, Y, for a period from 2000 to 2020. Now again, we have YIT equal to beta naught plus beta 1 XIT plus epsilon IT. Now we are interested not only in the relationship between X and Y, but we are also interested in the individual specific characteristics and the impact of these individual specific characteristics on Y. So in the earlier model of a fixed effects regression, we are trying to control for these so that we get the absolute effect of X on Y. But in the case where you are actually interested in these individual specific characteristics and what those individual specific characteristics have on Y, we use a random effects model. Now, given that the case, we would have to include that in the model as a variable, as a random variable, which is beta naught plus beta 1 XIT plus lambda ZI plus gamma ZI plus lambda PT plus epsilon IT. Now here I have taken the individual specific effects that are time invariant, and here I have collected the individual specific effects that are time variant, or they vary with time. So just as we controlled for those in the fixed effects model, here we include those variables or those random variables as a explanatory variable. so that we can also find out, along with the relationship with x to y, what is the relationship that these characteristics have on y. Now, in a random model, when we pick up the 4 districts A, B, C, and D, we assume that these 4 districts are randomly picked up from a population of districts. So there's an entire population of districts, and from those districts, 4 districts were randomly selected. And each district has its own individual specific characteristics that actually follow a normal distribution. Or these characteristics, like gamma and p, say gamma A, P A, gamma B, gamma A, okay, let's make it gamma A, or lambda A, and for each of these specific A districts, we have the individual characteristics that are also derived from a population of characteristics. So this is also randomly selected. We call this as a random variable. So these influences or these effects are actually random variables, and this sample is also a random selection from a population. So because these effects are randomly selected, or they are derived from a population and they're randomly picked from a population, there is absolutely no correlation between the error term and x. So as there is no correlation between the error term and x, we can actually include these characteristics as explanatory variables, and there will be no issue of multicollinearity. So we get the beta 1 value, say beta 1 value is 0.04, or sorry, 0.4. Beta 1 value is 0.4. So in this case, we say that a 1 unit increase in x leads to a 0.4 unit increase in y. And this is applicable not just for the sample that we selected, but the entire population of districts. So we can say that in general, or the average effect across the entire collection or population of districts, we say that x and y are related in such a manner. So we could say that if we are to run a random effects model, then we understand that, say we are trying to collect data of countries from 2000 to 2020. And instead of countries, say we focus on developed countries, or we focus on OECD nations, and then we collect the data from 2000 for all these. So in this case, when we are picking or randomly selecting countries from the whole population of countries, you have to run a random effects model, and whatever result you get will be applicable for all countries, not just the ones that you selected. Say you selected 10 countries. It's not just for the 10 that this beta 1 coefficient is effective, but we can say this relationship applies to the entire countries. But assume that you pick out developed countries, or you picked out OECD countries, or you pick out the districts in a particular country. Then in that case, you have to run a fixed effects model. And whatever result you get is applicable only to that particular sample that you picked up. It cannot be generalized. So that is why we say that random effects, the effects are random variables, and the coefficient represents the average effect across all the entities, and we assume that there is no correlation. So there is no correlation, and there's no multicollinearity in this case. So that is the difference between a random effects model and a fixed effects model.